So, welcome to the next lecture of differential equations. Today, we are going to discuss system of first order ordinary differential equations. Let me wait for the people. So, we have already discussed what are differential equations, how can we classify differential equations into major categories with respect to their order, degree, and linearity. We have also discussed the solution of first order differential equations, single first order differential equation, by using different techniques, for example, separable differential equations, linear first order differential equation, and then exact differential equations. So today we are going to discuss what are the system of first order differential equations and how we can solve them. So you can see on this slide we have a single first order differential equation which is given by this. dx by dt is equal to f of tx, where f of tx is any function of independent variable t and x. Sorry, where the domain of this differential equation is t from a to b. I hope you know it. Now, what if we have more than one differential equations, particularly of first order? So a system of two first order ordinary differential equations can be defined on some domain a to b. And now we have two first order differential equations. The dx1 by dt is equal to f1 of tx1 x2, and dx2 by dt is equal to f2 of tx1 x2. Now x1 and x2, they are two dependent variables and we have only one independent variable. That is, x1 and x2 are both functions of t. So for example, if we have this kind of system of two differential equations, the first one is a first order differential equation and the second one is also a first order differential equation. This differential system of differential equation, this one is basically a linear first order system of differential equations. Why it is linear? Because dependent variables in each term, they have degree 1. As we have discussed the linearity in the previous lecture, I hope you know what are the linear differential equations. Now another example is this one. It has also two first order differential equations, dx by dt and then dy by dt, and both equations are functions of tx, y, x here, y here, and sine t. This system is also a linear first order differential. Let me admit the other people. Yes. Now, this is again a linear system of first order differential equation because every dependent variable has degree 1. Dependent variable, not the independent variable. We don't see here because it is t is independent variable. So this is again a system of linear first order differential equation. Now the third example is this one, which is dx by dx1 by dt is equal to tx1 for x1 x2. Now you can see here there is a product of dependent variable. So the degree becomes here 1 plus 1, 2. So this equation is not linear. So the second equation, similarly, you can see that dx2 by dt is equal to x1 square, 5x1 square. So the dependent variable, degree of dependent variable is not linear. It is 2. So this example is basically a system of first order non-linear differential equations. I hope you got it. If you have any question, you just raise your hand and I'll allow you to ask your question. Now we go to the next slide. System of first order linear differential equations. For example, in uh, this one, this can be written in the matrix form. The matrix form, how can we write? The left hand side is written in this column matrix or the column vector dx1 by dt and dx. Yeah, here we must have dx2, we must have x2 by dt. So it's a typo mistake. And on the right hand side, we can write these coefficients, these entries, which are the coefficients of dependent variable x1 and x2 in the form of a matrix. You can see here that we have 3, 4 in the first row and 5 minus 7 in the second row. So here is again, I have a typo mistake. So here we must have 5, not 4. So this is 5 and 7. So any linear first order system can be written in the matrix form in this way. Now, see the second example. The second example is also a system of linear first order differential equation. We can write this in this form, in the form of a matrix. We can take the derivative outside and we can simply write x, y, the dependent variables in this vector, and this one we have a coefficient matrix which contains the coefficient of x, y, and then there is another vector, this one, which is not basically a coefficient of any dependent variable. We put it separately in the vector plus this vector. So this is again this system can also be written in the matrix form. Now, both these systems are linear first order system of differential equations. Now we have the third one, this one. This is not a linear, it is non-linear system of first order differential equation because of this product, and here we have square. Can we write this system in the form of a matrix? No, because we cannot take outside this one x1 here and we don't have x2 here. So here also we have x1 square. So we cannot write this system in the form of a matrix. So there is some question in the chat window. Kindly ask the questions of the previous lecture after this lecture. When we finish this lecture, I'll be available. You can ask me questions regarding the previous lecture. Now, another question, sir, isn't 8t cube non-linear in second example? No, it's not. 8t cube, basically in the second example, here you are talking this one. This is the coefficient, and this coefficient is basically, it involves only the independent variable, not the dependent variable. Linearity and non-linearity of differential equations we have discussed in the previous lecture. It depends on the dependent variable, not on the independent variable. So the degree of dependent variable y is 1 here. We don't look at the degree of independent variable. So t is independent variable. So it doesn't make this differential equation non-linear. Okay, we only see the degrees of dependent variable, not the independent variable, in order to check whether the given differential equation is linear or non-linear. Here you can see that in the third example, these two are dependent variables, x1 and x2. So both have degree 1, 1. So 1 plus 1. This whole term has a degree 2. This whole term. So that's why this differential equation is non-linear. Okay. And this is again non-linear because here the degree of x1, which is dependent variable, is 2. It is not 1. So in short, we cannot write a system of non-linear differential equations into a matrix form. This is not possible because we cannot separate this vector. or this vector in this system. I hope you got it. If you have any question, you can ask me. Otherwise, we are going to the next slide. There is a question in the chat window that if one equation is nonlinear, then whole system is nonlinear. Yes, of course. If one of the 2 or 3 or 4, any number of equations, if one equation is nonlinear, then whole system would be considered as nonlinear system. So next is first order systems notations. Now, in the previous on the previous slides, I have shown you only the system of 2 first order differential equations. But in fact, we can have a system of more than 2 first order differential equations. They might be linear, they might be non-linear. So in general, this is the general notation for the first order ODE systems, ordinary differential equation system. In general, if we have sorry, if we have n first order ODEs defined on some domain of the independent variable t from a to b, the first equation is this, second, and so on, nth differential equation. Now you can see here that x1 is dependent variable, but this right hand side function, it may contain x1, x2, so on, xn. So all the dependent variables. Similarly, dx by d2, dx2 by dt, it might be another function f2, and it may be a function of x1, x2, so on, xn. Similarly, the nth differential equation, which is dxn by dt, and it may have some different function of x1 to xn. So here is an important thing. These FIs, these functions, right-hand side functions, they may be nonlinear functions, they may be linear functions, as we have seen in the previous examples. Let me show you a couple of more examples after this. I'll show you some more examples after discussing these notations of n first order differential equations. Now, here, note that FIs are, they may be linear, they may be non-linear. Now, if they are linear, then their form, FI, if all the FIs, if all these functions, if they are linear, then the system can be written in this form. The x1 by dt, let me open it, that's one, yes. So dx1 by dt is equal to a11 of t. This is a coefficient function and it depends on t only. It is a function of t times x1, the first dependent variable, another coefficient a12 of t, it is only the function of t, times the second dependent variable x2, and so on. This function times xn plus some function of t which doesn't contain, which is not the coefficient of any dependent variable. In general, we write this in this way. So second differential equation can also be written in this form, a function which is a function of independent variable only, x1 dependent. Similarly, we can define all these terms and another function which is independent of dependent variable. So in general, we can write the nth differential equation in the similar way. So this is basically a system of first order, system of n first order differential equation, and this system is linear system because it has all the linear equations, because all the dependent variables you can see here in this system, all the dependent variables, they have degree 1. You can see here also all the variables have degree 1. So this is also called a normal form of the system of linear first order ODEs. Now this system, we saw in the previous example that this system can be written in the form of a matrix. There is a question in the chat window. What if there is a constant in the equation? Now this function may be a constant. It may be a function of t. It may be a constant as well. So any equation may contain a constant that will be treated as this function. Okay, I hope you got it. So now this system, as we have seen in the previous examples, here on this slide, this one, it's if we have a 2 by 2 system which is linear, which has all the dependent variables power 1, and it may contain another function which doesn't depend or which is not a coefficient of dependent variable, then this system is a linear first order system. This can be written in a matrix form in this way. Exactly, we have discussed the general system. Now this is what it may be some constant value, maybe 2 or -5. If we have here instead -2 or maybe +2, or here we have -5, then this will be a constant. And always any linear first order system can be written in the form of a matrix. Now let's see in the general notation how do we write this linear system, this one, in the form of a matrix. One more thing which is important to mention here, that is, if this one, if all the functions gi of t, where I from 1 to n, if all those functions are 0, if this is 0, if this is 0, if this is 0, then this system to here, this is called homogeneous linear system. Otherwise, it is called non-homogeneous linear system. I hope you got it. Now, this system can be written in the form of a matrix. If we assume that the x vector is this one, x1 of t, x2 of t, xn of t, and a of t is a matrix, which is basically the matrix of coefficient functions. There is a question. Why it is called homogeneous? It's a standard notation because if all these terms, if all these functions, they are 0, then we are left only with this system, which doesn't have any extra function which involves only t. Okay, if we don't have this vector in the system, the rest, the remaining system, we call it homogeneous, just to, you can say, recognize what are the homogeneous, because while we'll discuss the methods of solution of these systems, the solution of homogeneous linear system, we can find it in a different way, and the solution of non-homogeneous linear system, their solution have some different method. They have some additional steps to follow in order to get the solution of non-homogeneous linear system. We'll discuss in the next lecture how to solve these systems and what this function basically contribute towards the solution of these systems. I hope you got it. It's just a name, you can say. If we denote x by this vector, x1, x2, so on, xn, and the matrix A, which contains the coefficient of all the dependent variables, which are a11 of t, which is a function of t only, and a12, a1n of t, and so on, all these coefficients, which are basically the coefficients of dependent variable. You can see here, these are the coefficients which we put in the matrix, all these coefficients. Now, if we write the matrix A in this form, and the right hand side, you can say this vector f of t, which is basically f1 of t, f2 of t, fn of t, Instead, I should write here g1 of t, g2 of t, and gn of t in order to be compatible notation, in order to have compatible notation with the previous system, this one, because in the previous system I have used here g1, g2, gn. So I should write here g1 of t. I hope you got it. G2 of t and so on, gn of t. So then the previous linear system can be written in this form: d by dt. We take it common outside, and we write x1, x2, so on, xn. On the right hand side, this is your matrix, and this is your coefficient vector again, because x1 is multiplied with this one, x2 is multiplied with this one, and x1. So when we multiply these two, this matrix with this vector, we get the same form of n first order linear systems, plus this vector, the right, which is basically independent of dependent variables. So this should also have here g1, g2, and so on, gn. So the system of first order differential equation can be written in this form, in a matrix form, or simply we can write, we can simplify further the notation in this way: d by dt of x, because x is this whole vector, and a times x, here we have, this one is a and this one is x. So dx plus this vector, we call it f. So in short, the system of differential equation can be written in this form. There is a question in the chat window. Why is it called homogeneous? Will we have always have a scale matrix? Yes, in the system of first order differential equation, for now, in this course, we will discuss only those systems in which number of equations and number of dependent variables are same. So is not working, so it's back. Sorry. Let me clear this thing. The homogeneous system, I told you here, if in this system, if all these functions are zero, if there is no such kind of function, then we call that system a homogeneous linear system. A homogeneous linear system, it has some other definition also, uh, but for here, for the systems, you just remember that if this vector, if all these functions are zero, then we call the system a homogeneous. Otherwise, it is called non-homogeneous linear system. Now we go to yes, this one. Simply, we can write the linear system in this form. It is basically a non-homogeneous linear system, because here we have this term as well, f. If this f is zero, if this f is zero, then the remaining system will be called a homogeneous linear system. Or we can write more in a more compact form as x dash is equal to a x is equal ax plus f. Now let's go to the next slide, slide 7. Here are some examples of non-homogeneous linear system and homogeneous linear system. You can see here that if we have this system, dx by dt is equal to 6x plus y plus z plus t. This is and a term which contains only the independent variable. So dy by dt is equal to 8x plus 7y plus 10t, and z by dt is equal to 2x plus 9y minus z plus 16. So here is another term which is independent of dependent variables, means it doesn't contain any dependent variables. So when we write this system into a matrix form, we can write x dash is equal to, and the coefficient of x, y, z here 6, 1, 1, and similarly others, plus this term which doesn't contain any dependent variable. So this term is non-zero, so this system is non-homogeneous linear system. Now in the second example you can see that we have dx by dt is equal to minus 3x plus 4y minus z, plus there is no term which contains only t here, neither here, neither here. So this system is what? It is a linear, homogeneous linear system which can be written in this form, matrix form, or we can simply write it in this form: x dash equal to a times x. If you have any question, you can ask me. You just raise your hand, or you can type your question in the chat window. Now, if you don't have any question, we move forward. Now, what is the solution of these systems, whether they are homogeneous linear system or non-homogeneous linear system? So any vector x1 of t, x2 of t, xn of t, in short, we can write this thing as an x vector whose entries are differentiable functions, means the derivative of x1, derivative of x2, and derivative of xn, they exist, first derivatives. If we insert this vector into the system, first order system, then all the equations are being satisfied. Means this solution turns that system into identity equations, identical equations, you can say, as we have discussed the solution of a simple ordinary differential equation. So here we have a system, so system of n equations, so we must have n solutions. And whenever we insert all these solutions into that system, all the equations in that system should be satisfied. I hope you got it. Now, solution vector is basically that vector which satisfies all the equations in that system. Now, for example, if we have this one, how to verify the solutions. For example, if we have this example in which we have to verify that on the interval, this one minus infinity to infinity, let x1, which is 1 minus 1 and e raised to power minus 2t, and we can write this whole thing in this way as well by multiplying e raised to power minus 2t inside this vector. So we get this vector. Similarly, there is another solution vector x2 3 5 e raised to power 60, e raised to power 60 can be multiplied inside, so we can write the solution vector in this way. We have to prove that these vectors x1 and x2 are solution of this homogeneous linear system. We have to prove it that they are solutions of this system. So we check one by one. First we insert x1. First we insert x1 into this system, and then verify whether this satisfy all the equations in this homogeneous linear system. So in order to substitute x1 here, what we need the derivative of x1. So x1 dash is what? We take the derivative here, which is minus 2 e raised to power minus 2t, and the derivative of this thing is negative negative. So here negative negative positive 2 e raised to power minus 2t. And similarly, we need the derivative of x2, which we can take the derivative of this thing, which is 18 e raised to power 60, and 5 6 30 e raised to power 60. Now we have the derivatives. Now inserting this here, what we get, they have started with the right hand side, a times x. Here a times x is what? This is the a 1353 times x1. So what is x1? X1 is this. We inserted it here, and now we multiply with this matrix A with this x1 vector. We get these two entries, and finally we get this one and this one, which is equal to what? This is equal to what? This is equal to x1. You can see it. This is equal to the derivative. Question in the chat window. Now this is equal to what? Sorry, not that one. Now this is equal to what? This is equal to the derivative here, the derivative of x1. So what we have obtained here, this implies x1 dash is equal to a times x1. So this solution, this satisfies this system. So we say that x1 is the solution of the given homogeneous linear system. There is a question in the chat window. What is the question? Why we are solving it like this? It's just we are investigating whether what are the solutions are of what kind. This linear systems, they have solution vectors. Now we are trying to verify that these vectors are solutions. When they are solutions, when they satisfy the linear system. Later on, we will try to find these solutions by discussing different solution methods. -2 is an eigenvalue. We'll discuss eigenvalues and eigenvectors later on when we'll discuss the solutions of these systems. Okay. Now we try to verify whether this is also the solution of this system. We started with ax2. We inserted x2 here. So ax2, a times x2, we multiply it, we get this thing, which is what? This is equal to x2 dash. So this implies that x2 dash is equal to ax2. So what does it mean? It means that x2 is the solution of this homogeneous linear system. So this is what the solution of linear system. How to find them, we'll discuss it later on. Now we move forward to the next slide. Now, on the previous slides, we see what are the systems. Now we are going to discuss what are the initial value problems, which contains n first-order differential equations. So here, initial value problems means every equation in the system must have an initial value along with the equation. Let T naught be a point in the interval T naught, maybe usually the starting point. T naught should be A in most of the systems, but maybe it may be greater than A, but it should be within this interval. Now we define x of T naught is equal to x1 of T naught, x2, xn of T naught, and all this thing is equal to what? Gamma 1, gamma 2, gamma n, so gamma n. For example, we say that x1 of T is what? It is gamma 1. T naught. X2 of T naught is gamma 2, and so on. Xn of T naught is gamma n. So we have initial conditions along with all the equations in the system. Then the system is called along with these initial conditions. If we denote this one x naught, and if this is x naught, then this is basically a set of initial conditions. One initial condition with each equation in the system. Then this whole system is called an initial value problem. I hope you got it? If you have any question, you can ask me. Now, the next one is superposition principle. Superposition principle is always, or you can say it is only valid for the homogeneous linear system. Now, we have seen that in the previous example that there were two solutions of a single linear system. That was basically a 2 by 2 system, and that system has two solutions. So in general, a system which has n equations, it will have n solutions. So here we suppose that, or let x1, x2, and xn be the n solutions of the homogeneous linear system, this one. This is what? This is an n by n system because it has n dependent variables and there are n equations. So it will have n solutions. We say that x1, x2, so on, xn. These are n solutions of the homogeneous linear system, which is a n by n system. Then the linear combination of all these solutions, how can we write it? Linear combination, a constant times x1 plus constant times x2, so on, cn times xn. This is what? This is the linear combination of all these solutions. So what is superposition principle? If we have a system of n first order differential equations, linear system, and if it has n different solutions, then their linear combination is also a solution of the given linear system, homogeneous linear system. The superposition principle is only valid for, remember this, superposition principle is only valid for homogeneous linear systems. I hope you got it. There are questions in the chat window. This is always true for homogeneous linear systems only, not for non-homogeneous linear systems, because non-homogeneous linear systems they will be handled separately because their non-homogeneous part, which is basically g1 of t, g2 of t, those functions, the solution depends on those functions. On the solution, you can say, depend on the type of those functions in the non-homogeneous system. So this superposition principle cannot be proved for non-homogeneous systems. They can only, this principle can only prove for homogeneous linear systems. There is a question in the chat window: are all coefficients of different value? I don't get your point. Kindly explain your question. Another question, Shumail Sajid: constants can be any real number? Yes, these constants Cn, I have mentioned here Ci, where I from 1 to n are arbitrary constants. So this is called the principle of superposition. And I repeat, this is only valid for homogeneous linear systems. There is a question: is only x1 is equal to c1 times 1, c2 times 2 a solution? Superposition principle is basically also valid for single first order differential equation. We have discussed this. A single differential equation cannot have more than one solutions, means general solutions. So if we have a system of two differential equations, then there might be more than one solutions, and we can write them. We can write a linear combination of those solutions to get this kind of solution. that is valid only, valid for system or differential. But in this case, you cannot, Muhammad Abdullah asked a question, you cannot write the solution in this way, C1 times constant and C2 times constant, because you can see here that these x1, x2, xn, these are solution vectors, and these vectors contains how many components, how many elements? N elements, because this linear system is basically x is a vector of n cross 1, and this whole system is basically n cross n system. This A matrix basically is n cross n. Therefore, the solution vector must be n cross 1 vector. Is there any other question? Let me check. No. So I repeat here, what is the superposition principle? If a system of n first order linear homogeneous linear system has n solutions, then the linear combination of those n solution is another solution n. This is called the superposition principle. I hope you get it. If you have any further question, let me check the chat window. Batul, you have asked some question? No. Okay. Then we are going to the next slide, this one. For example, this example is basically related to the superposition principle. We will discuss, there is a question in the chat window. Is this a general solution? We'll discuss the definition of a general solution in the next slides. Now, example of superposition principle is that if assume that this x1 and x2 are two different solutions of this homogeneous linear system, then we can prove that the linear combination of x1 and x2, which is defined in this way, this is again the solution of this homogeneous linear system. How can we verify it? I hope you know how to verify it. We have discussed one example regarding the verification of solutions. You multiply, you insert this x here, you multiply it with this matrix A, you must get the derivative of this x. The derivative of x is equal to right hand side. So we can verify that this linear combination is also a solution of the given homogeneous linear system, this one. I hope you can do it. There is a question in the chat window. So didn't you say that every linear system will have one solution? I didn't say this. I did not say this. Any linear system, if we have, I said, if we have only one equation, first order, linear, then that can have only one general solution. But here we can have more than one solutions for n system of n first order differential equations. Now, next one is, I hope you get this. If you have any question, otherwise we are going to the next slide, slide number 13. What is the linear independence and dependence of these solutions? I told you if we have a linear system of n differential equations, then it will have n solutions, x1, x2, xn. Now, whether these solutions are linearly independent, then this set of solution vectors is linearly dependent if there exist constants c1 to cn, such that if we write this system c1 x1, c2 x2, cn xn, and we put it equal to the zero vector, This is what? This is a homogeneous linear system. We have discussed linearly independent solutions in the previous lectures. I hope you know this. So in order to check whether all these solutions are linearly independent or not, we write such kind of expression, which is C1 x1, C2 x2, Cn xn. We put it equal to 0 vector. And this is what? This is a homogeneous linear system. If we solve this homogeneous linear system and we get all the C's 0, then if after solving this solution, after solving this homogeneous linear system, if all the constants they are 0, C2 is equal to 0 and so on, Cn is equal to 0, then we say that this set is linearly independent. Otherwise, this set is linearly dependent. Or you can say that if at least one of these C's, C1, C2, Cn, if at least one of these C is non-zero, then we can say that this set is linearly dependent. We have already discussed these things. I hope you get it. Is there a question in the chat window? Sir, didn't you say that every linear system will have one solution? No, the statement is incorrect then. What? Then the set is linearly dependent if there are constants such that if all the constants are 0. Yes, this or all are, here we must have non-zero. Or you can write here linearly independent, not dependent. You cross it. There's a typo mistake here. We should have here linearly independent. I hope you get it. The question in the chat window. Can you please repeat what you said about the value of coefficient? Yes. This set of vectors, which is a solution of this system of homogeneous linear system, this set will be called linearly independent if we consider such an expression or an equation C1 x1 plus C2 x2 plus Cn xn is equal to 0. If all the constants, or after solving this, if all the constants Ci's they become 0 or they are 0, then we say that this set is linearly independent, not dependent. If at least one of these C is not 0, then we say that this set is linearly dependent. We have discussed linearly independent and dependent sets in linear algebra when we discussed, I think, vectors and vector spaces. I hope you remember that. If you have any further question, you can ask me. Is there any question in the chat window? I hope you get it. We are going to move forward now. Now, if in the linear algebra we discussed that this set is linearly independent by considering this kind of expression, which is a homogeneous linear system. That is easy to solve. This homogeneous linear system is easy to solve when these x1, x2, and xn, they contain only real values. They contain only constants. But what if these x1, x2, xn, they are basically functions of t? Then it will be very difficult to solve this homogeneous linear system, because you have seen that the solution of this kind of homogeneous linear system, its solution, for example, here, this one, x1 may be a function. It may contain a function of t in each entry. Here, this one, you can see here cos t, sin t, cos t, sin t. The other one is also, it contains a function. Now, whenever you write a homogeneous linear system of this kind, this one, it would be very difficult to solve this homogeneous linear system. Now, what we do in this case, we use the Wronskian in order to check whether this set x1, x2, xn is linearly independent or not. Now, what is Wronskian? If we have x1, a vector which is defined in this way, x1, x21, xn1, and x2 is x12, x22, and so on, xn2, and similarly we can define xn, which contains x1n, x2n, xnn. Now, these are these functions. They could depend on t. Means x1n. It may be a function of t, as we have seen in the previous example. If these entries, they are functions of t, then it would be difficult to solve that homogeneous linear system, which we have discussed on the previous slide. Now, what we do in this case, how do we check whether these vectors are linearly independent or not? We calculate their Wronskian. Now, how to calculate Wronskian? We put these vectors here, these column vectors here, here, and then here, as the column vectors of this Wronskian. This is what? This is basically the notation of Wronskian, Wronskian of x1 vector, x2, and so on, xn vector. The first column contains the first vector, the second column contains the second vector, the nth column contains the nth vector, solution vector. Now, Wronskian is the determinant of, basically, determinant of these column vectors for every t in that term. For every t in the domain, if this Wronskian is non-zero. Wronskian means if this determinant is not equal to 0, then we say that these vectors are linearly independent. There's a question in the chat window, sir, how do we get more than one solutions for solving a linear system? We will discuss this. For now, you just assume that there are n solutions for a system of n first order homogeneous differential equations. Here you assume that there are n solutions. How to find n solutions? We will discuss this in the upcoming slides. You would get it. Okay, don't worry. We will discuss how to find solutions of these systems and how much solutions we can obtain. We'll discuss in detail everything. Now, I hope you get it. What is the Wronskian? If we have n solutions, we put all these solution vectors into a determinant, this one. If determinant is non-zero, then we say that all these vectors x1, x2, xn, they are linearly independent. Next, we are going to know on the next slide 15. Here is an example of Wronskian. On the previous slide, we had discussed an example, and we have proved, we have verified that x1 and x2 are two solutions of this homogeneous linear system. We have verified this. Now we are going to prove that these two solutions are linearly independent solutions. How to check this? We put these vectors, solution vectors, we put these two vectors, this one and this one, into the column vectors of the Wronskian here. This one is the first one, and here is the second one. Now, if we solve this determinant, you can see that we obtain 8 e raised power 4t. How do we obtain this? We just multiply this one and this one, and minus we multiply this one and this one. After simplification, we get 8 e raised power 4t. Now, you can, I hope you know that exponential function is never zero. It is never zero. Whatever the value of t is between this minus infinity to infinity. So whatever the value of t belongs to this set on the entire real line, this Wronskian is non-zero. If it is non-zero, then we can say that these two solutions, x1 and x2, they are linearly independent. I hope you get it how to verify or how to find that the solution vectors are linearly independent or not. If this Wronskian is zero for at least one value of t, then we cannot say that these vectors are linearly independent. They will be linearly dependent. This Wronskian should be non-zero for all values of t in the domain. Okay, if for at least one value it becomes zero, then we cannot say that these two vectors are linearly independent. So I hope you get it. Remember this one. Next is fundamental set and general solution. Now, what is the fundamental set? The definition is any set x1, any set which contains the n linearly independent solution vectors of the system of first order differential equation, homogeneous system of first order differential equation. If these are x1, x2, and xn are n linearly independent solutions or independent solution vectors of the homogeneous linear system 5, which I defined on the previous slides, on an interval, then this is called fundamental set of solutions. It's easy. If we have n solutions, if they are independent, how to check them, whether they are independent or not. We find the Wronskian of these vectors. If the Wronskian is non-zero, they are linearly independent. If they are linearly independent, we call that set a fundamental set. There is a question in the chat window. E raised power, so isn't it e raised power minus infinity equal to 0? Yes, e raised power minus infinity is 0, but e raised power minus infinity is not included in the domain here. You can see here, you are talking about this thing. It is e raised power minus infinity is 0, but t belongs to open interval. This one, t cannot take value of minus infinity or plus infinity. So t should be less than infinity and greater than minus infinity. Okay, I hope you get it. So the next one is, yes, fundamental set. What is fundamental set? If a linear system has n independent solution vectors, then that set is called fundamental set. And how to write the general solution? If x1, x2, xn, they form a fundamental set of solutions of the homogeneous linear system. This is only valid for homogeneous linear system. We are talking about only homogeneous linear system. If this is the set of fundamental solutions of the homogeneous linear system, then the general solution can be written in this form. General solution is this one, and it is what? C1 times x1 plus C2 times x2, and so on, Cn times xn, where Ci's are any arbitrary constants. They could be real numbers. I hope you get it how to find the general solution of I hope you get what is the general solution of homogeneous linear system. If x1, x2, xn, these are n solutions, and this is a fundamental set of solutions, then the general solution can be written in this form. Now, still, we haven't discussed how to solve homogeneous linear systems. We have assumed that these are the solutions, and we can write the general solution of the homogeneous linear system. Now, we are going to discuss how to find solutions of homogeneous linear systems. Let me now we are going to discuss how to solve first order system of ODEs. Particularly, first we shall discuss how to solve homogeneous linear system of first order ODEs. Homogeneous, I repeat here, we will discuss in this part how to solve homogeneous linear first order systems. Now, I hope you remember how what was the normal form? What was the normal form of the system of homogeneous linear first order differential equation? This one, yes. This is the system of normal form of system of homogeneous linear first order ODEs, and this can be simply written in this form by using the vector notation or matrix notation. This was just I repeated here just to remind you. Now the next one is here in the system you can see that the coefficients of this homogeneous linear system, they depend on t. Okay. All these coefficients are functions of t. Now, what if we have the same system with these coefficients as constants? On the next slide, I have repeated the same system, but here now you can see that the coefficients are only the constants. They are real numbers. They are no more functions of t. First, we shall discuss how to solve system of homogeneous linear first order ODEs with constant coefficients. These coefficients are all constants. They are not functions of t. Means here the coefficient matrix A is basically its entries are now constant. Constant means real numbers. First, we will discuss how to solve this homogeneous linear system whose coefficient matrix only has constant entries. I hope you get it. Now, on the next slide, I have given you a couple of examples which later on we will solve them. Homogeneous linear system with, you remember that the coefficients are now only constants. These are constants, and we can write this homogeneous linear system into this form. Now the matrix A is only, it contains only the real numbers. The entries are constant. So this is a 2 by 2 homogeneous linear system, and this is a 3 by 3 homogeneous linear system, whose coefficients are basically here the real numbers. Now this can be written in the matrix form in this way. Now we shall discuss in this lecture how to solve this homogeneous linear system with the entries in the matrix, with the constant entries in the matrix. Okay. Now, how to solve them? This is the question: how to solve these linear systems? If I'm going to start with the single equation. single first order homogeneous linear differential equation. You can see that this is a single equation. Dx by dt is equal to 4x. This is homogeneous and this is again linear because x power 1, x power 1 here. If we solve this first order homogeneous differential equation, it's a single differential equation. How do we solve it? We can separate its variable. We can use the technique of linear equations to solve it. Whatever the technique you use, we'll get the same answer. Now, I am going to separate the variables of this differential equation. So I can divide this x on the other side here, and I can multiply dt here on this side. So the variables have been separated. Now after integrating, what we get 1 over x integral dx for integral dt. Now integral of 1 over x is what? It is log of x, and here we have 1, integral of 1 is t plus some constant. Now by using the property of log, we can write x is equal to e raised power this thing, e raised power 4t plus c. Now separating this term and this term, we can write e raised power 4t times e raised power c naught. Now c naught is what? C naught is a constant of integration. So e raised power c naught is again a constant. So I can put this thing equal to some constant c. And in general, this solution can be written in this form: c times e raised power 4t. Now, whenever we have a single homogeneous linear first order differential equation, its solution is of this type. A constant times exponential of some constant time t. You remember the form of this solution: a constant time exponential of constant time t, where t is the independent variable and x is the dependent variable. C is the constant of integration. Now, let's see the form of the general solution for system of two homogeneous first order ODEs would be the same. The form of the solution. We can see that if we have a single differential equation, the form of the solution is this constant times exponential term. Now, let's look at the system of two differential equations. We have verified in the previous slides that this x1 is this x1, which is written in the form of a constant time exponential term. We have also verified that x2 is the solution of this homogeneous linear system, and it has a form, a constant vector times exponential solution, exponential term. So whenever we try to solve a homogeneous linear system of two equations, we have a constant vector which contains two entries and times exponential function of t. Similarly, the x2 is the solution of this homogeneous linear system. It is also of the form constant time exponential term. Now, in general, homogeneous linear systems, they have basically a solution of this kind: a constant vector, a vector which contains constants, times the exponential of lambda, some constant lambda, times the independent variable t. So in general, we can write this solution in this form: ki, where ki is a constant vector times exponential of some constant time t. So in general, we can write, if we have a system of n differential equations, homogeneous first order, then the solution of this system must be of this kind: constant, a vector which contains constants, times exponential of some constant time t. In general, we can write the solution of the homogeneous linear systems in the form of this expression, which is a constant vector times exponential. This is always true. Now, what if we insert this here in the given homogeneous linear system? This is a solution basically. We are going to insert this into this system. If we insert x equal to k times e raised power lambda t here in the derivative, we have to take its derivative. So its derivative is what? K is a constant. E raised power lambda t. What is the derivative of this thing? It's lambda times e raised power lambda t. So we used it here, lambda k times e raised power lambda t, and the right hand side we inserted just the solution, just this solution, a times k times e raised power lambda t. So what we have done here, we inserted this into this equation. We get this. Now we know that e raised power lambda t is known to you always, whatever the value of t, we can cancel e raised power lambda on both sides. If we can cancel, we can get this thing, lambda k is equal to ak. Just give me a couple of minutes, then I'll finish the lecture because this time is up. Just 1 minute. So this equation now, here we have a lambda times vector. Here we have a lambda times vector and matrix time vector. Matrix time vector is a vector, and here we have a vector. So vector can be equated to a vector. But if we want to take this k common in these two expressions, we take this thing on the other side, we take this thing on the other side, we get lambda I k minus a k is equal to 0. We have written here I. Why we have written here I? It's the same logic as we have discussed while discussing the eigenvalues and eigenvectors of a matrix. Because now we are going to take this k common, and we get lambda minus a times k is equal to 0, which is what? This is a homogeneous linear system. This is a homogeneous linear system which can only have non-trivial solutions only if the determinant of this coefficient matrix is 0. I hope you remember we have already discussed these kind of things in eigenvectors and eigenvalues. Now, if a homogeneous linear system has a solution of this kind, whenever we insert this into the homogeneous linear system, we obtain, what do we obtain? We obtain a homogeneous linear system of this kind, and this homogeneous linear system, from this homogeneous linear system, we can find k. From here, we can find k, but we can only find non-trivial k if this homogeneous linear system has non-trivial solutions. And when this homogeneous linear system has non-trivial solution, when this coefficient matrix is basically is singular, its determinant is equal to 0. So from here we can find eigenvalues corresponding to A, and then we can find eigenvectors, the corresponding eigenvector from this equation, as we have calculated eigenvectors and eigenvalues. In the previous lectures, we have discussed how to find eigenvectors and eigenvalues. Now we have similar kind of homogeneous linear systems and a characteristic equation. What we had called it, this is basically characteristic equation. We find eigenvalues from this equation and eigenvectors from this equation. We'll discuss how to find, and I'll give you a couple of examples for this in the next lecture. So today we stop here. If you have any question, you can ask me. There is a question in the chat window. Let me stop the recording. Okay, guys, see you in the next lecture.